sharing this QR code, and we will look at and continue with doing what we have been covering so far. Yesterday we did two examples on how to solve the energy balance using heat of reaction method. Today we're going to continue, but we're going to look at it from another method, which is the heat of formation method. And this heat of formation method, okay, yeah, there. You can see the screen now. If you are using this heat of formation method, the reference state is very, very different. That makes you can see the very because it's from you're getting the heat of formation, so you have to start from the elemental element, the elements itself that occur naturally in nature. So, for example, in this example, we talked about that yesterday. Here, reference state must be carbon because you have propane there. Yeah, when you have propane, you know you have carbon, you have hydrogen, so you need hydrogen. Hydrogen occur naturally as a hydrogen gas, carbon as a solid. So your reference state must be from the elements that occur naturally. That's the difference from the previous example that we did yesterday. When we did the previous example, we used the component as the reference state. For example, you use propane as the reference state, propane gas. You use oxygen gas. You use carbon dioxide gas. You use water vapor as the reference state. But when you're using the heat of formation method, as the name itself, formation, that means you have to start from the element. You have to start from the basic element. So in this case, you have propane, so you start with carbon, solid carbon. You start with hydrogen gas, and for example, you have water. So you have to have hydrogen gas and you have to have oxygen gas in order to form water. What else do you need? Of course, you have over here nitrogen, but actually nitrogen is not involved in the reaction. Nitrogen is just an inert, but you still have to list it down in your reference state because it is an inert. So you list it as okay, just forget about that statement. You list everything based on its element state. Okay? You list it as how it occur in nature. You cannot list your reference state as propane. You cannot do that because you are using the heat of formation method. That's the very big difference from the previous method that we did yesterday when we were looking at heat of reaction. So when you're using the heat of formation method, again, the temperature is at 25 and 1 atm because the data that is in appendix B1 is at that temperature, that standard temperature of 25 degrees C and 1 atm. And another thing that I want to highlight to you guys, there's a typo error in the note is okay, the equation when you're doing using the heat of formation, this is more or less the equation. I will show you guys how we arrive to that equation, but there is this term that is not supposed to be there. That B is not supposed to be there. So do that. Please correct that. Correct that typo error. Okay, so let's do this example. This is the same example that we did yesterday. Same example, but now we'll be looking at it from the heat of formation method. So I'll be going back to my example, the previous example yesterday. This was the example that we did propane yesterday. We did it using the heat of reaction. We calculate the heat reaction yesterday. I forgot what we got, but it's somewhere here. Where is it? Is this the one that we did yesterday? Yeah, this is the one that we did yesterday. Yeah, we got the table fill up. So I think we got the heat of reaction yesterday too, but somehow I did not have it written down. Not sure why. And what did we get for the answer? We got this as the answer yesterday. So now we're going to do the same example, but we're going to do it, approach it using the heat of formation method, and we will check whether we get the same answer as what we did yesterday. So let's have a go at heat of formation. So this is heat of reaction. So when you do the heat of reaction method, just now I pointed out that your reference state, when you do it using the heat of formation, you use whatever component that is listed in the process. You have propane, you have oxygen, you have carbon dioxide, you have water vapor. For example, if you want it to be water, liquid water, then you have it listed as liquid water. If you want it to be water vapor, as is coming out here in your process, then you can also list it as water vapor. But the most important thing is your heat of reaction must be available. Because the equation, when you're using the heat of reaction, the equation to solve for your Q or your heat is equals to the change in the enthalpy is equal to extent of reaction times by the heat of reaction. So you really need to know your heat of reaction in order to use this method, which is a heat of reaction method. So out your molar flow rate times by the corresponding enthalpy, and the summation inlet your molar flow rate times by the corresponding enthalpy. So this is the equation that you're going to use when you're using the heat of reaction method, because you will have over here the heat of reaction. But when you are going to do the heat of formation method, when you are doing your heat of formation method, so I'm going to write here heat of formation method, the same example, we're going to solve it using heat of formation method. Or the equation now is much simpler. You only need to solve for the or heat that you need your equation, your outlet, the summation of your outlet, your molar flow rate times by the corresponding specific enthalpy minus the summation of the inlet by the for the product of the molar flow rate and the corresponding enthalpies. So this is your equation now. There is no longer any term for heat of reaction in this equation. So when do you use this method? When you don't know what is the heat of the reaction. For example, this example just now, you don't have the value for the heat of reaction. But over here you do have for the equation written. So since it is given explicitly, it's given there, you don't need to calculate it. Then you will use, the first thing you check is for the heat of reaction. If it's available, then you will use the heat of reaction method. But for example, if it's not available, then either you need to calculate it, you know how to calculate it, because we have covered that in the earlier part of this chapter, how to calculate the heat of formation of the reaction method. But if you don't want to calculate it, or you just cannot simply calculate it, you just cannot calculate it, then you have to use the heat of formation method to solve for the energy balance. So now, if you go back to the equation just now, this is the equation for the heat of reaction. That's the heat of reaction method. You have this term over here. You have the heat of reaction. So when you don't have the heat of reaction, then you'll be using the heat of formation method, whereby you don't really need the reaction at all. Let's solve the same problem. We're going to do the whole thing all over again. I don't think I need the whole line. How many rows do I need? 1, 2, 3, 4, 5, 6. I need 6 rows. So 1, that's 1. That's 2, 3, 4, 5, 6. Okay, I have my component. I have propane, oxygen, nitrogen, carbon dioxide, hydrogen. I still have to list the component as they are the same as the heat of reaction method. The component are listed the same as the heat of reaction method. It's just that the reference state, they are not the same. I need to write down there is propane, gas, I have, let me just without going scrolling up and down. I have oxygen gas. I have nitrogen gas. Beside that, I have carbon dioxide gas, and I have water vapor. Okay, so I'm going to get one. Is that straight? Not straight. Undo that. Well, that's the best. Okay, molar in. What's the unit? The unit is it mole per second. The unit is mole per second. This is the same values that we have yesterday. It's just that we are using it. We're going to solve it using the heat of formation method instead of the heat of reaction method. So this is out mole per second, and you have your enthalpy out with the corresponding unit of kilojoules per mole. Okay, so let's fill up the molar flow rate. For propane coming in is 100. It's the same as yesterday, so don't worry about this. You can still use your own table that you have yesterday. It's just that we're going to solve it using a different method. So there's no carbon dioxide in the inlet. There's no water vapor in the inlet. So and every time there's no substance or no component in the inlet or outlet, just put a dash there. Okay, now we have the unknown H1, your enthalpy cap H2, your enthalpy specific enthalpy H3, your outlet for your propane, with no propane coming out, is completely consumed. You have oxygen coming out 100 mole per second. Beside that, the amount of nitrogen, which is the inert, is coming in as the amount of inert. It should be the same as inlet and outlet. So the amount is 2,256. Beside that, you have carbon dioxide coming out 300, and you have your water vapor 400 mole per hour. So we're going to find the enthalpies for oxygen H4, nitrogen H5, your specific enthalpy for carbon dioxide, and lastly you have your specific enthalpy for your water vapor. So just like I mentioned just now, your reference state is not going to be the same as when we're doing it using the heat of reaction method. So your reference state, if you look at the component, you have propane, so you're going to have C, solid, hydrogen gas. It existed naturally as a gas, so you're going to write it as hydrogen gas. You're going to have oxygen gas, which occur naturally in nature. You have nitrogen gas, and what else do you have? You have, that's it, isn't it? That's it. That's simply all the elements that is going to make up your components. So the temperature is going to be at 25 degrees C and 1 atm. So that is going to be your reference state. Right? So when you do this, you start from the basic element. For example, you're going to get, in order to get enthalpy H1, you start from C, solid, and hydrogen gas at 25 degrees C. This is more or less like constructing the hypothetical path. At 25 degrees C, 1 atm. Okay, that is your starting reference state. So your propane, let's go back to our diagram. We need to show at what temperature it is. Okay, your propane this is your propane coming in at 100 mole per hour. The temperature is at 25 degrees C, 1 atm. When you solve the problem using the heat of reaction, you listed that propane as the one of the reference states at the same temperature as the inlet and the outlet. It so happened that at the same temperature, which is 25 degrees C, 1 atm, because that is where your heat of reaction is at. So when you listed propane as one of the component as that of your reference state, so automatically, since it is at the same temperature as that of your reference state, your enthalpy is equal to 0 when you did it using the heat of reaction. Now the problem now is that when you do it using the heat of formation, you do not have any propane listed as the reference state in the reference state. Propane is not listed in the reference state. It doesn't exist as propane. The component, not the component, the elements are the one that existed as the reference state. For example, carbon solid, hydrogen gas. So what you have to do is from your element, you should form your compound, which is in this case your propane gas. At what temperature is it formed? It is always formed at this standard temperature and pressure. Okay? So that is what you're doing here using the heat of formation. So from step 1, which is your element, your carbon, your hydrogen gas, you're going to form your propane. This is actually your heat of formation, which you can get from appendix B1 for propane. Yes. Okay, so your H1, this is your H1. This is your H, which is your reference H, and that is going to be 0. Because that's where you state your reference, your carbon, solid, your hydrogen gas at 25 degrees C. At that point, it is 0. So when you reach your 25 degrees C at 1 atm, that is your H1. So happen that H1, let's scroll up, your propane is at this temperature, 25, 1 atm. Okay. So how to get that value? You should be going to your, looking up the appendix for B1. So let's go to B1 for propane. So where is my appendix? B1. So let's look for propane. Is this B1? Yes, this is B1. If you have any question, please raise it. Do not just keep quiet if you don't understand, because it's very important. You will be asked for both methods. I'm very sure of that. It's either the test or one of it is coming out in the final. If you are asked for the test, in the final. So propane is here. This is propane. Okay, so your heat of formation is this column. The only thing is that, is it liquid or is it gas? So in our example, the propane is in the gas phase. So since it is in the gas phase, this is your heat of formation for the gas. Yeah, minus 103.8 in kilojoules per mole. So let's go back to our example. That is going to be, let me write, okay, minus 10, what did I write just now? 3, so 108, 103 minus 103.8 kilojoules per mole. So that is your H1, minus 103.8. Any questions so far? We are forming propane from the basic element, which is carbon, solid, and hydrogen gas. Right, so that's easy. So let's look at H2. If you have any question, please raise it up. For H2, you're looking at oxygen. Your reference same as the component itself. For example, this is your component, not the component, that is oxygen, and your reference is also oxygen. So in this case, you can use appendix B8 to get the data, because your appendix B8 is also at 25 degrees C and 1 atm. Yeah, you can use the appendix B8 from your appendix, from the textbook. So now, what temperature is oxygen at? We need to get the temperature. The temperature is 300. So this is 300 degrees C and 1 atm. So both oxygen and nitrogen, they are both at 300 and 1 atm. So we're going to go from our reference state of 25 degrees C to 100. 300. So your oxygen gas at 25 degrees C, 1 atm, you're going to just simply heat it up to 300 degrees C and 1 atm. You could use the appendix B1 using the polynomial equation by integration to get that value of H2. So this is your H2. This is your H reference. This is 0. You can use either method. You can use appendix B1 or appendix B2, but the appendix B2 will involve integrating, so that is a hassle. So how about we just use appendix B8? So let's go to the appendix. Let's look at appendix B8 for oxygen. You are not forming oxygen here because oxygen already existed the same as in nature as oxygen gas. So you don't need to form it anymore. It's already in its natural state. So let's look at B8. Anybody has any question?
Doctor,
Yes.
so we only do it whenever we have a compound, right?
Yes, that's right. Because you are starting from the element, so you need to form the compound first.
Thank you.
You're welcome. Good. I like that somebody asked a question because, or else I'll be speaking. I don't know whether you are paying attention or not, whether I'm just speaking alone. Okay, now we reach this appendix B8. I already highlighted it here because we did it yesterday. So for oxygen, the value is 847. That's the same value that we got yesterday. And it's going to be the same today because your oxygen existed as a gas in its elemental form. So you don't need to form it anymore. It's already in its elemental form. So that is 8.47. So I'm going to go back to my example. I'm going to list that is equal to 8.47 kilojoules per mole. So you just simply read it from appendix B8. You don't need to.
Doctor,
Yes.
may I ask you?
Yes, please.
For the reference state for the heat of formation, so always will be 25 degree and 1 atm?
Yes.
Okay.
Why? Because your heat of formation from the appendix, let's go to the appendix again. Your heat of formation, if you look, oh dear, I need to scroll up again. So no problem. Just scroll up. Just bear with me. We're going back to appendix B1. I need to point out that the heat of formation is always at 25 degrees C and 1 atm. The standard temperature for this is not STP, guys. Do not get mixed up with STP. This is not STP. This is just simply the standard heat where the reaction occur. So this is your, let's highlight it. Okay, let's zoom in. This is your heat of formation. And that superscript there implies that it is at 25 degrees C and 1 atm. That's why your reference state is always at 25 degrees C, 1 atm. So let's go back to our appendix B8. Why I need that? Because I still get more values from that appendix B8 in order to complete the table. Okay, so this B5, B6, coming. Okay, it's almost there. Okay, here we go. Alright, so we need one more for nitrogen. Remember, nitrogen existed in its natural state as nitrogen gas. And we also happen to have that component in our process. So at 300 degrees C, the value of nitrogen, the enthalpy for nitrogen at 300 degrees C is 8.12. So I'm going to write that in our example. So this is nitrogen. Oops, I always happen to forget about that. 8. What did I mention just now? 8.12. Okay, 8.12. And this one just now, the value for oxygen just now is 8.47. I got it there. Excuse me. Yeah, we completed one column for the inlet. Now we need to do the rest for the outlet. Excuse me. Okay, so now look at for H4. Yeah, I'm going to zoom out. H4. Remember, the outlets, the component are coming out at a temperature of 1000. So all of these components coming out at 1000 degrees C, 1 atm. So for H4, we're looking at oxygen gas, you start from the reference state. So the reference state is oxygen gas at 25 degrees C, 1 atm. So when you start there at that reference state, of course, your enthalpy is equal to 0. You are going to form, or are you going to form, or are you going to heat up oxygen, guys?
Heat up.
Heat up. Okay, good. Because oxygen already existed in that form. In the elemental state, it is the same as in the process. It's the same. So you don't have to form it. So you're going to have oxygen gas at 1000 degrees C, which is the temperature of the outlet at 1 atm. So again, you can get that value, your enthalpy H4 from appendix B8. So this is the same value that we got yesterday. Yesterday, when we were looking at this value, we got 32.47. Right, the same value from appendix B7. So, sorry, B8. I got the wrong info. Appendix. It's B8. So at 1000, that's the value 32.47 for your oxygen. And if you do the same thing for nitrogen, that's going to be 30.56. I'm going to put that value 30.56 for our nitrogen. So nitrogen 30.56. We got that from appendix B8, the same as what we got yesterday. And for our oxygen is 32.47. Now I just show you guys how to get that value from appendix B8. So now we are left with
Doctor.
Yes.
Sorry for interrupt. For H1, the heat is of formation is at 25 degree C, right?
Yes.
Shouldn't we add another heat from 25 to the inlet temperature?
Inlet temperature, you mean, for propane?
Yes.
Okay, now let's go back to our diagram. Please have a look at what temperature propane is in. Okay.
Yes.
Okay. Good.
Thank you.
Welcome. Thank you very much for the question. And now we're going to look at H6. Yeah, H6 is for carbon dioxide. It's a compound. It's not existing in its elemental state. Carbon dioxide is not an element. It is a compound. So you have to form it first from your elements that is available, that you have registered as your, that you have listed down as your reference state. Your elements, they are your carbon solid and your oxygen gas in order to form carbon dioxide. So your H6 has to form carbon dioxide first. After that, you heat it up. Once you have formed it, you need to heat it up. Okay, so let's do H6 then. I'm going to zoom. Okay, I want to see both the table and to show you how we're going to do to get the enthalpy. So for H6, okay, you have. I'm not going to write for H5 because you know that you're going to get it from the appendix B8. So I just wrote down the value from appendix B8 for H5. So now we're looking at H6. So we have carbon dioxide. So you start from your element, carbon solid. You have oxygen gas at the reference temperature and pressure. So at that reference, since you stated it that is going to be your reference state, so that is your enthalpy is 0. So now we're going to form first your carbon dioxide gas at that same temperature, 25 degrees C, 1 atm, because your standard heat of formation is at that temperature. So you're going to get that value from appendix B1. Okay, that's going to be a gas. So that is going to be, we're not going to write that enthalpy there. We're not going to write the enthalpy there. I should not be writing that because your final enthalpy is the one over here. Gas at 1000 degrees C and 1 atm. So that is your final enthalpy, which is H6. Okay. So what's going on over here is that you form your carbon dioxide first. After that, you heat it up. So let's give this a symbol of submission. Sorry, your subscript 1. So in order to get H6, it should be the sum of the heat of formation for carbon dioxide gas plus the extra enthalpy for heating it up from 25 to 1000 degrees C. So in order to get that value, this delta H1, where can you get it, guys? What is the change in the enthalpy from 25 degrees C to 1000 before heating?
Integrate, right?
Integrate, yes. From what temperature to what temperature?
5 to 1000.
1000.
Thank you very much. Thank you. So what we're going to get the polynomial coefficient from appendix B1. Sorry, B2. If I have a look at the what I have over here, I'm not going to show you guys the appendix B1. I'm just going to list down the value from appendix B1 so that we can save some time from looking back and forth. So for carbon dioxide, your A is 36.11 times 10 to the power minus 3. Your B is 4. I'm just going to list it down for you guys, but you can go ahead, please look it up in the appendix because you do happen to have the textbook with you guys, so you should look it up. Minus 8, that's P squared. I'm out of space. Okay, that's P
Doctor.
squared. Yes?
Actually, CO2 is in table B8. We can get it from table B8, right?
Yes. Yes, we do. Is it available in B8? Let's see. Of course, it's at same temperature as B8. The reference state is 25 and 1000 I think is also in B8. So let's look at the appendix B8. Yes, you have carbon dioxide. Thank you very much. Thank you for pointing it out, or else we'll be spending time integrating. So that is 48.60. That's 48.60. So we'll be putting that as our delta H1. That's 48.6. It's not H6, guys. It's not H6 because you need to form it first. So that is 48.60. Thank you very much for pointing that out. But if you don't have it in the appendix, you'll be integrating it. Okay, hold on. Okay. This is what I was going to do just now. Let me finish this. If you need to integrate, let me finish this just for in order to show you guys what we have to do. If you don't have it in any sources, it's not available anywhere. So this is what you have to do. You need to integrate it. Okay? So when you integrate, you should be getting the same value just now as that of the 1048.60 from the appendix B8. Okay? This is kilojoules per mole. Same thing as what you should be getting if you integrate it or if you're getting it from appendix B8. So now you sum it up, your carbon dioxide. If you look it up in the appendix, your heat of formation, let's go back for carbon dioxide heat of formation in the appendix. We'll be going to appendix B1. Carbon dioxide, I'll be rushing through this. Sorry if it's it's not pleasant to look at. With the scrolling up and down. Okay, this is B2. So B1 is here, carbon dioxide. Okay, guys, take note. I'm not going to go back and forth. I want you guys to note it down. Okay, for water, the heat of formation of water, sorry, that is not heat of formation. That is not heat of formation. This is still B, is this B1. Where is my B2? Is it? Not B2. Where is heat of formation? Where is heat of formation? Okay, there is heat of formation. Okay, for water, we're going to list down for water, the heat of here is the heat of formation, guys. We are forming what gas. That is your heat of formation. Okay, so not this one, not that value. Okay, so write it down because I'm not going to go back and forth, scrolling up and down. It will be a lot of time. It will be too much time consuming there. So for the heat of formation of water, because we're going to form water also, for gas, water vapor, that is going to be minus 241.83 the unit kilojoules per mole. So that's one of the heat of formation that we need. Besides that, we need the heat of formation of carbon dioxide. Okay, propane, we already have it down. He already listed it down. The heat of formation of propane just now, when we did the H1 for propane, gas, the heat of formation already Yes, you guys, it's now minus 103.8 same unit kilojoules per mole. Now the heat of formation of carbon dioxide, write down for carbon dioxide. So we're going to search for carbon dioxide. Okay, your carbon dioxide is going to be, where is your carbon dioxide? There you are, carbon dioxide, that's carbon dioxide. So your heat of formation for gas, minus 393.5 kilojoules per mole. So please write that down because I'm not going to scroll up and down, but I still need to go back to appendix B8 because I still need that extra information there. Okay. Oops, I went too far. Okay, this is appendix B8. Let's go back to our example. Just now, I need the heat of formation. I'm going to erase this. I need my heat of formation for carbon dioxide. So I already got, I got it. Minus 3, I thought I did not write it down. So this is what is given in appendix B1. So your H1 just now, we just got it from appendix B8 plus 48.60. So what is your final value for H6? Sum it up, please. Minus 393.5 plus 48.60. What is your answer?
Minus 3, 44.9.
Minus 344.9. Thank you. So that will be kilojoules per mole. You will write that in our table for H6 minus 344.9. Okay. Lastly, we have to solve for H7. Now, this is now the equation I pointed out when I was introducing to you guys the heat of formation method. This is actually what we are doing. The equation is like this. If you want to find the enthalpy, you have to get the heat of formation first. That either you cool it down or you heat it up. So from your reference state of 25 degrees C to the whatever temperature you want, you use your CP for that component, integrate it. So that is more or less what we did just now. Yeah, which is for this part, you need to integrate. For your heat of formation, you can get it from your appendix. So that is more or less your equation whenever you do the heat of formation method in order to get your enthalpy. So let's look at the last enthalpy. The last enthalpy is H7 for water. Yeah, so H7 for water. You have water. You need to form water first. In order to form water, it's a compound. It's a vapor. You need hydrogen gas plus oxygen gas. You don't need to balance your equation because you're not going to do any. You're not going to use any coefficient. You're not going to balance it. So right now, actually, these two compounds should be at 25 degrees C, 180 M. That is at your reference. That's your reference state, which is oxygen. Okay, oxygen and hydrogen there, in order to form your water. So now what you have to do is form your water from your element of hydrogen gas and oxygen gas. So your enthalpy here, because it is at your reference state, is going to be 0. The formation is going to be at the same temperature, 180 M and 25 degrees C and 180 M. After that, because your outlet, your product is coming in at coming out at 1000 degrees C, so you have to heat it up from 25 to 1000 degrees C. So that is your vapor. So over here you have your heat of formation for water vapor. Okay, and over here you have your heating that you need to carry out. And for water, it's also listed in appendix B8. So you can get this from appendix B8. You don't need to integrate. And your heat of formation for water, just now I asked you guys to write it down, is minus 241.83 kilojoules per mole. So now let's go to our appendix B8 in order to get the change in enthalpy for the heating process. So we already have here water at 1037.69. So it's 37.69. So let's go back. So that's going to be 37.69. So if you do the sum, your enthalpy 7, this is enthalpy 7, is going to be your heat of formation plus the change in enthalpy for the heating process. So this is going to be for water vapor. So that is going to be minus 241.83 plus 37.69. So you should come up with a value of what, guys?
Minus 204.14.
Thank you, Sulaiman. 0.14.
Yes.
Okay. Thank you. So that's kilojoules per mole. So now we already completed our table. So that's minus 204. Minus 204.14. Everything is there. So now the final step is to solve for the energy balance. And please, whenever you solve for energy balance, please write the full equation. You have to write the full equation. And any terms that you drop, you have to give your reason for dropping it. Yeah. Or else you might be missing. You don't get, you'll be penalized for not giving the reason. So this will be dropped. Your kinetic energy, your change in kinetic energy, your change in potential energy, and your work shaft is going to be 0. Give the reason. The work shaft is 0 because there's no moving parts involved. Your kinetic energy because there's no change in velocity. Your potential energy because there is no change in elevation. So that's very short. You don't need to write too long on that. So your final equation is going to be your heat loss or heat gain is going to be the change in enthalpy. Since you're going to use the heat of formation, that is just outlet, the sum of the product of your molar flow rate with the corresponding specific enthalpy minus the inlet with the sum of the product of your molar flow rate and the corresponding enthalpy. So now let's look at the table. We have to zoom out. I can't seem to be able to have both. It's too long. I need to have the table in display, and at the same time I need to write down the solution. So I'm not sure whether I can do it over here. Okay, let's do it using this equation over here. Because or else I will not have the table in view, and I need the table to be in view. Yeah, I'm going to erase this so that I will rewrite it. Yeah, so that it will be, I have enough space. You should be also be calculating it now that everything is, the table is completed. You should be able to get the answer based on the equation here. So now, just look at the outlet. We have 100 mole times by its corresponding enthalpy. For oxygen, for nitrogen, 2,256. I'm covering the table. You're not looking at, you can see the table, but I can't see because I've got my hand on top of it. Okay, so 300 carbon dioxide minus 344.9 of the corresponding enthalpy. And for water, you have 400. Your inlet. Your inlet, you have 100 grams of propane times by negative 103.8, its enthalpy, plus 600 mole per second of oxygen gas, 7, plus the last value, which is for nitrogen, 2,256 times by its enthalpy, 8.12. So now close the bracket. That is for your outlet. So what is the final value of your heat? Yesterday, what we got yesterday, we managed to get 1.62 negative 1.62 times 10 to the power of 5 kilojoules per second. So your unit will be kilojoules per second. This is how you use the heat formation method. Not that difficult actually. You just have to remember that you need to start from the elements. You cannot start from the compound. Your reference state must start from the elements. Then you form the compound. After you form the compound, you either heat it up or you cool it down. That's all. In order to get the enthalpy. So anybody managed to complete the calculation? I will also do the calculation. we will get could be faster than you guys or anybody that managed to make it faster than me. So give me the value.
Doctor,
Mm-hmm.
I got the same value as yesterday's.
Yeah, what is it? Negative 1.26 times 10 to the power 5, isn't it?
Yes.
Yeah. So you will get the same answer. It's just a matter of which method you like. Do you like the heat of formation method or do you like the heat of reaction method? But if you don't have the heat of reaction, there's no way you're going to use the heat of reaction method. Yeah. So any question, guys? This is your final answer.
Doctor,
Yes.
can you
Yes.
please show the solution of yesterday?
Okay. This is the solution of yesterday. Yeah. So that's the final equation. So this is your final answer. What the difference is that your reference state is different. Your reference state is the same as the component that existed in the process. Your reference state at the same temperature, 25 and 1 atm. That's the same. It's just that your component propane existed as is listed as the reference state. Your carbon dioxide is listed as the reference state. Your water is resisted as the reference state. It could be vapor, it could be liquid. I pointed out that yesterday. So the reason why it's listed as liquid over here because you're going to use this equation whereby it is present as liquid. So that's why it's written down as liquid. But if you don't have it, if you wanted to calculate it using vapor, then you have to calculate your heat of reaction here for the second equation. Okay? So the very distinctive difference between this method, heat of reaction, and the heat of formation is your reference state. If you're going to use the heat of reaction, you need to have your heat of reaction available. If you don't have it available, if you can calculate it, okay, fine, you can use your heat of reaction. But if you can't you just cannot calculate it and it's just not available, then you cannot use your heat of reaction. So whenever you don't have any information on the heat of reaction, then you have to use the heat of formation method. Okay? Let's point out about the reference state. When you're using the heat of reaction, you can have the compound listed as the reference state. And it can be at 25 degrees C, and it's always at 25 degrees C and 1 atm because the reaction, the standard heat of reaction is always at 25 degrees C, 1 atm. Right? But if you're going to use the heat of formation, just like the name implies, it has to be formed. And in order to form it, you have to start from the elements that occur naturally. Carbon solid occur naturally. It doesn't propane doesn't occur naturally. It has to start from carbon and hydrogen gas. Hydrogen gas occur naturally. Oxygen gas occur naturally, the same as nitrogen gas. Right, so you still have the temperature at 25 and 1 atm for the reference temperature and pressure. It's just that you just have to start from the element. So now you ask about anything else that you need to ask about this method. So this is the equation. When you're using the heat of reaction, you have this extra term that you have to add to the summation, to the equation. You need to find the extent of reaction to multiply it with the heat of reaction. Anything else you need to know? Guys, anything else you need to know? Anything else that you want to ask? You still need appendix B8. It's not that you need to integrate some of it. It doesn't, sometimes you need to integrate if it's not available in appendix B8, but in this example, you can get it easily. It's given directly in appendix B8. It's available, so just get it from appendix B8. And fortunately for us, the reference state is the same as 25 degrees C and 1 atm for appendix B8. Any other questions? Guys, any other questions? We did this in 50 minutes. No, less than that, because it's already 250 now, 51. So it's less than that. Any questions? Your compound, even though you're using the heat of formation method, you still list it as it is. You know, you do not write it as carbon in this column. You still list it as propane, oxygen gas, carbon dioxide, water vapor. It still existed as that in the process. It's just that your reference state is going to be in the element state. Any questions? Okay, it is quite easy this method. You just need to look it up. A lot of data in the appendix. That's all. No questions? Just remember this equation. Okay, if there's no question, I would like to do another example. This example is, if I'm not mistaken, this is the example. Okay, whenever you have two reactions occurring simultaneously, the best method would be to use the heat of formation. It's easier. Or if you're going to use the heat of reaction, then you need to find the heat of reaction for both reactions. So that involves extra calculations. Okay? But since the heat, because you have two reactions, it's better to use the heat of formation. So you don't need the heat of reaction here. I'm not saying you cannot do it. You can do it. You can do both methods. It's possible. In fact, it's really possible. So it's just that it's far easier if you're using the heat of formation. So in this case, you have methane gas reacting with oxygen being burned to form formaldehyde and water gas. The same methane is going to react with the same oxygen, but now it's going to form carbon dioxide and water vapor. So over here, you have the material balance done already, completed. You don't need to bother with the material balance. All the products has already been calculated, the values of the number of mole. So we will skip that part, but still, I forgot this again, that when I did that example just now. Please write down your basis. So write down, for example, 100 mole of methane. Write down the chemical. Don't just write 100 mole. What 100 mole? It should be 100 mole of methane. Please write that down. Right? Because I came across somebody's writing in the second test 100 mole. Mole of what? Because you have more than two inlets. I mean, more than one inlet. So you need to specify. Okay, so all this has been completed for you guys. So now what we have to do is going to do the energy balance using the heat of formation method. I'm going to go straight into this example. We're not going to take a break because it's so that you're quite fresh with the method. Okay, so that's, I'm going to construct myself or build myself my table. Trying to get a straight line, but I did not manage to get a straight line. Oops, not doing a good job here. Okay, it's okay. So how many components do I have? I have oxygen, methane, 1, 2, 3. I have formaldehyde, that's 3, 4. Of carbon dioxide, 5. Water, 6. Yeah. Not straight at all, but okay. It's slanting actually. Not doing a good job here. It's slanting. I have a 1, 2, 3, 4, 5, 6. One more column, one more row. Okay. So I have my chemicals, methane, gas. I'm assuming it's a gas. Yep, it's a gas. I have oxygen gas. I have nitrogen gas. Beside that, I have my formaldehyde also as a gas in a gas phase. I have carbon dioxide gas. And I have my water vapor. Okay, so that is my first column. I have my molar flow rate. Is in molar? No, it's not. It's not flow rate. It's just mole. Okay. Now my enthalpy in. I need to write that down. In. So that will be kilojoules per mole. And my out. Mole per mole. I mean the rate. Not the rate. It's actually amount. That's out. Enthalpy out. That's kilojoules per mole. Okay. So what are the temperatures? Okay, take note of the temperature coming in, 25 here, 100 here, 150 there. Okay. So what reference state? So I'm going to erase this. I need to write down my reference state. As you just as what we have done in the previous example, your reference state must be the elements because you're using the heat of formation. So you're going to have C, solid. You're going to have hydrogen gas. You're going to have oxygen gas. You're going to have nitrogen gas. What else do we need? That's it. Okay, you have your carbon, your hydrogen, your oxygen, and your nitrogen at 25 degrees C and 1 atm. Okay. So let's put in the values for the flow, the amount coming in. That's 100. Your oxygen 100. Your nitrogen 376. There's no formaldehyde in the inlet, no carbon dioxide, and no water vapor. Okay. So for the out, 60 mole of methane coming out. That means not all of methane is going to be consumed. You have some leftover of methane. You have formaldehyde, 30 mole. Your carbon dioxide is 10 mole. I'm looking at the block diagram. Your nitrogen is obviously going to be the same inlet and outlet because it's not really participating in the reaction. How about your oxygen? You're going to have 50 mole of oxygen in the outlet, and you have what else? You have your water vapor, that's 50 mole. Right? So write down the enthalpy: H1, H2, H3, H4, 5, 6, 7, 8, and lastly 9. Okay. That's a lot of calculation that we have to do. Okay, so your methane is coming in at 25 degrees C. Even though your methane is coming in at 25 degrees C, but because your reference state does not listed methane as one of its components, so this cannot be equal to 0. Even though methane is coming in at 25 degrees C and 1 atm, assuming everything is at 1 atm, excuse me, you still cannot have your enthalpy 1 equals to 0 because your reference state does not listed methane as one of the component, okay, as one of the reference state. So this one cannot be, H1 cannot be 0. Excuse me. So we start all over again for H1. That is for methane. So you start from C and hydrogen gas. So 25 degrees C, 1 atm. This is the last time I'm going to show you guys this, but you know how we come across this. We did an example just now. So it should be, we don't even need to construct this. We don't need even to write this. You guys know this is going to be the heat of formation. For methane. I'm just showing it again. So this is going to be methane. Yes. At 25 degrees C, 1 atm. Why at 25 degrees C at 1 atm? Because it formed at that temperature. If you need further, the temperature is not the same as your final temperature that you desired, then you need to cool it down, you need to heat it up. For it so happened that your methane is coming in at 25 degrees C. The feed is coming in at 25 degrees C for methane, so that's where you stop. So your heat of formation for methane, you need to get it from the appendix. So I'm going to list down all the heat of formation here. I'm not going to go back and forth looking at the appendix. I have methane, yes. I also have the heat of formation of, I need formaldehyde gas, the heat of formation of carbon dioxide gas, and I need the heat of formation of water gas vapor. Okay, previously we did the for water. I still have the value for water over here. It's negative 241.83 from the previous example. For carbon dioxide, also the same, 393.5 which we got from the previous example. And for methane and formaldehyde, we still need to look it up. So let's go to appendix B1. We can do a rapidly scroll it up. For those of you guys, you have your textbook, you can look it up in appendix B1. So we need formaldehyde. Where is F? So there is there formaldehyde. Yeah, there is formaldehyde here. This is formaldehyde. So that's formaldehyde. The heat of formation for gas. In fact, there's only one listed, minus 115.90. So I'm going to write that down because I forgot. So the heat of formation for formaldehyde is equal to minus 150.90. Right? What else do we need just now? We need the heat of formation for methane. So let's look for methane. For methane, this is methane. So the heat of formation for methane gas, negative 74.85. So that is the heat of formation for methane. Okay guys, so now we're going to go back to our example. I'm going to write down for methane is negative 74.85 kilojoules per mole. And for formaldehyde, it's negative 115.90 kilojoules per mole. Okay. Now, I'm not going to draw the whole thing. I'm not going to do the hypothetical path. We know that we're going to get the enthalpy using this equation, the heat of formation, plus whatever that needs to be heated up or cooled down to from whatever temperature you need. Okay, to the desired temperature, from 25 degrees C to the desired temperature. So now let's, we already managed to get for H1, the heat of formation of methane is negative 74 for H1. This is your H1 actually. I don't want to write that there. I really don't want to write that there because I will need it again. There. For H1, the heat of formation, this is H1, is equals to negative 74.85. So write that in our table. Okay, for H2, you start at 20, you start from oxygen because you are looking at oxygen now. You also have oxygen as the reference state. So you don't need to form any oxygen. You are just heating it up from 25 degrees C to the temperature that is given, which is 100. For oxygen, the inlet temperature is 100. So we can get that from appendix B8. Okay, the same as what we did just now from appendix B8. So H2, you can get it from appendix B8. So I'm going to go back to appendix B8. This is okay. We're going to go scroll all the way back to appendix B8. Yeah, here we are. Oxygen at 100. So this is 100. Oxygen 2.24. I'm going to write that down. Oxygen 2.24. Nitrogen, I need also for nitrogen 2.19. So this is for nitrogen. Because both of them is coming in at 100 degrees C. So let's put in these values in our example because have a look here. You have oxygen, you have nitrogen coming in at 100. So I'm going to write down that same value from the appendix. That's going to be 2.24 for oxygen. Oops. And for your nitrogen, 2.19. That is for 100. Your outlet is at 150. Sorry, I should not close that. Okay, 150. And if you go back to the appendix, you're not going to have any 150 listed. It's not listed down at 100. It's 150. It's somewhere between 100 and 150. So you need to interpolate. You need to interpolate somewhere here. Interpolate. Okay? So for nitrogen and oxygen, you need to interpolate. So let me erase this. Let me erase. Okay, so you need to interpolate between 100 and 200 at 200 and 150. You need to interpolate between that two values for your oxygen and nitrogen. Besides that, what else is coming out that we can get from appendix B8? Okay, we have carbon dioxide and water. So you have to interpolate also for carbon dioxide and water vapor. Okay, at 150. So they are also listed in your product. Water, vapor, carbon dioxide, and nitrogen. So you guys need to let me just display on my computer so that I don't need to go back and forth. I need to have the view of appendix B8 visible so that I can don't have to go back and forth. Hold on. I need to have it available. Okay. Hold on. Okay, guys, I'm going to go back to the example. Now let's look at. Sorry, anybody? Any question?
Yes, I interpolated already.
You didn't play. Okay, good. Yeah, good. Oh, sorry.
For N2, it's 3.6.
Okay, hold on. Let me write it down. 150 degrees C for N2 equals to Ayman?
For O2, it's 3.775 for O2.
Okay. O2. Okay, it's not N2. It's O2. There is O2. Sorry. It's the H
3.775.
37. Sorry.
3.775.
Okay. 3.775. That's kilojoules per mole. How about for nitrogen?
For CO2, it's 4.99.
4.99. Okay.
For H2O, it's 4.275.
Sorry again, can you repeat that again?
4.275.
Okay, thank you. And lastly, for nitrogen, what did you get? Nitrogen.
Sulaiman mentioned 3.66.
0.66.
0.66. Thank you. I did not hear that just now.
Thank you.
So thank you very much. So let me tidy up a bit. I just want to rewrite the oxygen here. Okay. So that is at 150. After you have interpolated, that's the value. Let's see whether we're not going to plug that values directly into the. Are we going to put that value into the process? Are we going to put that values into the table, guys? Somebody, what is H5? What is H5? Somebody? What is H5? I can't hear you. It's broken. H5 is actually for oxygen. So for oxygen, H5 is 3.775, isn't it? Oops. Okay. Is that correct, guys? Somebody respond. Is that correct?
Yes.
Okay. For nitrogen just now, after you have interpolated it, it's 3.66. We can plug it directly into this table. We can write it down into this table because we are not forming it. It's already in its elemental state. It's already in its elemental state. You don't have to form it. So that's why we're putting the numbers the values directly from Appendix B8. Okay. So for carbon dioxide, can you put in the value that you just gave me just now? 4.99. Can you just put it inside this table?
No, no.
No. Why
Yeah.
not?
Because we can like form carbon dioxide by hydrogen and oxygen.
Yeah,
Okay.
because you do not have it listed down as carbon dioxide here. You do not have it listed down as carbon dioxide here. So that's the reason. The same as water vapor. You do not have it listed down in your reference state. So you cannot plug in the values that you gave me just now, and you cannot use that value that you gave me just now and fill out the table. You cannot use that value. You have to start from your element first. You have to form it first. Okay. So for H7, H8, and H9 and H4, you need to form it first. Okay, so you'll be going back to this equation, which is that equation. You need to form it first. Okay, so now let's look at H4. Let's look at, for example, carbon dioxide first, H8. Okay, H8, which is for carbon dioxide. Your carbon dioxide is coming out at 150. Your carbon dioxide is coming out at 150. Your enthalpy that you need is H8. So you start using this formula, using that formula. Your heat of formation for carbon dioxide, just now I asked you guys to list it down. The heat of formation for carbon dioxide, so I'm going to just put it here, negative 390.5 plus from 25 degrees C, you are going to go to 150 now because your product is coming out at 150. So you are going to look at for carbon dioxide, H8. So your carbon dioxide from 25 to 150, that's the value, 4.99. So what's the final value? Minus what? Somebody give me a value. I'm using this equation to get the value of H8. Negative,
Minus 388.51.
sorry,
51.
0.51. Thank you. Kilojoules per mole. So I'm going to write that down. The value for H8 is 388.51. Yeah. Anybody getting a different value? Anybody getting not the same as 388?
Doctor.
Same, thank you. So we do the same thing for H4, for H7, and H9. Just that it's a different component. So now for H4, that involves methane. So we're going to look at the same equation just now. The same. I'm looking at this equation. This equation. So the heat of formation of methane, I wrote it down just now. So heat of formation of methane is negative 74.85. I asked you guys to write it down because we don't want to go back and forth. Now, we need to go from 25 degrees C to 150 degrees C. The problem is you cannot get methane that is not available in Appendix B8. It's not there. Methane is not listed in Appendix B8. So you need to get the CP of methane gas from Appendix B1. So if you look it up, I have that you still need to look it up in Appendix B1. So let's go to Appendix B1. We need to look up methane. A lot of scrolling up and down, but we cannot avoid that. So appendix not B1, B2. Sorry, B2. We need to get the coefficient of the polynomial equation. Okay, methane. This is appendix B2. So let's look for methane. This is methane. Okay, so it's yes. Form equation form 1 degree C. We're not going to use Kelvin. So these are the coefficient that we're going to use. So I better write that down because I might forget. So my A is going to be 34.31. My B is 5.469. My C 0.3661 and my D is negative 11. Yeah, so it's in the form of equation one. So we know what equation one is. We have been using that. So now we're going to put in the values of the coefficient in our equation. 34.31 times 10 to the power of negative 3 plus 5. I'm trying to squeeze everything in so that I can have it in one line, but I'm not sure whether it's possible. 0.366 1 times 10 to the power of negative 8 3 square. I cannot make it in one line. Plus, not plus minus 11 times 10 to the power of negative 12 to the power of 3 with respect to temperature. So after you have done that, you need to sum it with the negative 74.85. So what is the final answer? Somebody please give me the value. Is it 4.9 kilojoules per mole? Because from your textbook, the answer is 4.90. Is it 4.90? Somebody check. Do your integration using your calculator. It's a very straightforward calculation. Is it 4.90? Somebody? 34.31 minus 3. Hold on. Forgot the integration. How you guys are doing the integration? I'm not waiting for somebody to get the answer.
Doctor, I got 4.889.
889. Okay, thank you. So it's 4.889. They round it off. 4.889. Okay, thank you. So finally, our enthalpy for enthalpy 4 is minus 74.85 plus 4.889. That will give us a value of negative 69.961. That is the value for enthalpy 4. So I'm going to write that down in the table. Negative 69.961. Okay. We do the same for enthalpy 7 for formaldehyde. So you use the same equation over here. That equation, the heat of formation for formaldehyde is now listed it down. It's negative what? Oops, I think I'll do this. Negative 115.90. That's the heat of formation. I'm using that equation plus the integration from 25 degrees C to your final temperature of 150 degrees C. So for formaldehyde, I still need to look it up from appendix B, B2, the CP of formaldehyde. So let's go back to the appendix. Formaldehyde. So where is formaldehyde? That's M. So I need to look up for F. There you are. That's formaldehyde. So it's gas. Equation 1. We see that's your coefficient. So there's 0 there. So I need to write that down. As I need to remember. So I better write it down. 34.28, 4.268, and lastly, negative plus 0. I don't forget the 0. Negative 8.694. Okay, I'm going to go back to that example. So for this equation, we have 34. 44.28 times 10 to the power of negative 3 plus 4.268 times 10 to the power of negative 5 t. You don't have the t to the power of 2 there because it's 0. So you are left with the final d 8.694 times 10 to the power of negative 12 t to the power of not 2 but 3. With respect to temperature T2. Please calculate it. If I look at the answer from the textbook for formaldehyde, that answer, the textbook give a value of 4.75. The textbook gave a value of 4.75. So see whether you can get the same value of 4.75 after you have done the integration. Guys,
Yes, it's the same, Doctor.
Thank you.
4.75.
Good. Thank you very much. So now sum it up. Negative 150.9 plus 4.75. You end up with negative 111.15. That's the joules per mole. So that is your value for H7. Write that down. Negative 111.15. Lastly, we have the last enthalpy H9. That's for water vapor. Again, we'll be using this equation, okay, the one that I highlighted over here, that equation. We're not going to construct our hypothetical path because we know it's based on this equation. That's our heat of formation of water vapor. Heat of formation of water vapor, we have negative 241.83. So we need to go from 25 degrees C to 150 degrees C. Get the CP if you need it with respect to temperature. But then, since water vapor is available from appendix B8, so you don't need to integrate. So you just simply plug in the value from the appendix B8. So I'm going to erase this. We know we have that value just now, which is, you guys gave me that value for water. That's it, 4.275, going from 25 degrees C to 150. So 4.275 over here. So finally, you get your answer. When you sum it up, negative 241.83 plus 4.275, you will end up with negative 237.5 kilojoules per mole. Now putting in the values, putting that value here in our table. Yeah, we have completed our table. Right? So finally, we'll be able to solve for the energy balance. So I will erase this. Need space actually, but I don't have enough space. Are you guys? What you have to do next is come up with your equation. You need to write the full equation, but I'm going to just give you the final equation. That's out. Your N. The product of in is enthalpy. Now, what you have to do is get everything, summation up, and you should be able to get your answer. So, I don't have enough space. I need the whole table in view. So, let's see whether I can do it slowly. I need to scroll up and down. But I will be looking at the textbook for the final, for the outlet 60 mole. I'm looking at the textbook. I'm not sure our answer is the same, the enthalpy is the same for us. 59,961. For the oxygen is 50. 2.775. That's not the value, the values of the enthalpy is not the same as the textbook. For nitrogen, The enthalpy of nitrogen is 4.655 listed in the textbook. Here we have is it 4? Is it 3.66. Yeah. Some more, we have our formaldehyde, 30 mole. And we have negative 111.15 plus our carbon dioxide, the value of carbon dioxide is 10 and is corresponding enthalpy 388 point, what did we get? 51 because the textbook listed 2.88.6, we got 388.51. And lastly, we have our water vapor, 50 mole. The enthalpy negative 23, what did we get? 237.5. Okay, so that's for the outlet. Now might deduct from it the inlet. So we have the methane, the amount is 100. This corresponding value is enthalpy 74. That means that if H1 should be the heat of formation. So that is 74.85 plus the amount of oxygen coming in and its corresponding value of enthalpy 2 point, that's H2. Where is our H2? 2.24. Plus lastly, the amount of nitrogen and its enthalpy 2.19. Okay, we completed the equation. So now just plug it in your calculator and see what is your heat or the amount of heat that is going to be released or going to be absorbed.
Doctor,
Yes.
I got negative 15.292 times 10 the power of 3.
Okay. How about the rest of you guys? Negative 15.292 times 10 power 3. That's Aiman, is it?
Yes, doctor.
Yeah, because I did not, your name is not being displayed. I just recognize your voice. So the textbook gave a value of negative 15,300, rounded it off. That is the value from the textbook. Aiman gave me a value of negative 1,292. That's the amount of heat being released for these two reactions occurring simultaneously in the reactor. Anybody
Doctor,
else getting a different answer? Make sure. Sorry?
I got the same as Ayman's.
Yes, Faisal? Yeah,
I got the same as Ayman's.
your internet line is very poor. Okay, good. Oh, that's clear. Just now it was broken. Good.
Okay.
How
I got
about the
the
rest
same
of you
answer
guys?
as
I hope.
Ayman's.
Good. Yeah. Loud and clear, Faisal. Faisal, you are in UAE.
Sorry?
Sorry. Huh?
I didn't hear you.
Are you? Faisal?
Huh? Yes.
No. Okay. Yes. I was asking. Where are you now?
Let's
No,
chat.
no, I didn't.
It's lagging.
Any question?
Doctor, your voice is lagging.
Daunting. It's really because I have to experience. I got do it with the equation, and finally completing your table. And once everything is completed, it's all about solving your energy balance. Any questions? No,
Doctor-
good. Faisal, your internet line doesn't. Yes, Ayman.
Why can't we add
Yes.
the compound CH4 or H2O in the reference state?
Why? Because you are using the heat of formation method. You can use the compound as your reference state if you are using the heat of reaction method.
Mhm.
If you're using the heat of reaction method, yes.
So heat of
Yes.
reaction already includes the heat of formation, right?
In the heat of reaction method, you need to use a different, the heat of reaction method is, you need to have the heat of reaction for the first equation and the second equation. You need to find the extent of reaction for number 1. You need to find the extent of reaction for number 2. If you're using the heat of reaction method, your final equation, let me write the final equation. If you're using heat of reaction method, it's going to be like this. Okay, you have this, and after that you have as normal. This is your different from the outlet and the inlet. Okay. So you have this extra term when you're using heat of reaction. So you have that summation because you have more than one reaction. You need to get the extent of reaction for both reactions. Okay, you
So
have that extra term. Yes.
can we say that heat of reaction is basically the heat of formation of CH4 or other substance? Because we will only calculate for delta T.
Delta T.
For
Calculating the enthalpies, you mean?
yeah,
Okay.
enthalpy.
If you're using this method, your reference state is going to be, let me write down. Reference state will be methane gas. You're going to have oxygen gas. Going to have nitrogen gas, formaldehyde gas, and carbon dioxide, and water vapor gas. Water vapor, all of it at, okay, I need to erase my line. All of it at 25 degrees C and 180 M. So when you do this, it's sort of like the same, but you don't have the heat of formation. You only need the heat of formation in order to get that, your heat of reaction. That is when you need your heat of formation. You form the product, you have the coefficient, the heat of formation, minus your reactant, your coefficient, and your heat of formation. That is where your heat of formation comes into, in order to get your heat of reaction. But when you do the table in order to get the enthalpy, it's not about heat of formation anymore. Huh?
Yes.
So you're looking at the heat of formation when you want to get the heat of reaction. So in this case, for example, you have methane, and methane happen to be coming in at 25 degrees C, then your enthalpy 1 will be 0 because it's coming at 25 degrees C. Right? Because you have listed it as methane in your reference state. Therefore, oxygen, you can use appendix B8 to get that value, no problem. For nitrogen, you can get it from appendix B8 also. Yeah. Then you have your formaldehyde, but your formaldehyde, you cannot get it from appendix B8, you have to integrate it. Therefore, you need to integrate it. Sorry, this is not the, I got the wrong column. Should be here. Yeah, this is N. This is the enthalpy. Okay. So I'm trying to point out the difference. If you're using the heat of reaction method and you're going to use the heat of formation method, it's not the same. The reference state itself is already the very obvious difference. Right? So if you say, let's say this is N out, this is H out, this is H in, this is in. Okay, so let's say this is going to be 0. I'm going to write it so that it will not be missing. Okay. That is going to get directly from appendix B8, but at 100 degrees C. Isn't it? 100 degrees C, is it coming at 100 degrees C? Yeah, it's coming at 100 degrees C. So you can get it directly. So this 100 degrees C is 2.24. It's still the same. That will be 2.24. 2.24. For nitrogen, again, B8 at 100 degrees C. And still going to be the same as what we got in this example. Same. The one that we did using heat of formation. Now, for this part, we're going to get it from B8 at 150 degrees C. And that's the difference. Okay, now, N2 at 150 degrees C, just now you gave me that value. Where is it? Okay, N2 at 150 degrees C is 366. I'm going to write it down as 366. Is it the same or is it different from the previous heat of formation method? It's the same, isn't it?
Yes, it's
The same because you're not forming compound, sorry, you're not forming compound there. It's the same. All of this you can get from B8 at 150 degrees C. Somebody is super excited. So 25 degrees C to 150. LCP for methane. We need to integrate that. So if we did that just now, didn't we? We did that just now for methane. What did we get from methane? For methane, yeah, we did this. That part is 4889. 4889. So that answer will be 4889. That's the difference. Yeah. So for your formaldehyde will be integrating from 25 degrees C to 150 degrees C, Cp, dt. So the answer when you do that for formaldehyde, we did that just now. Where is it? Where is it? Yeah, this part. 475. 475. Okay, and lastly, you have what? You have your methane, your formaldehyde, you have your carbon dioxide. Dioxide, you can get that from appendix B8. B8, you can get that from appendix B8. And water vapor, the last component, also from appendix B8. That's B8. You can get that from appendix B8 at 150 after you have interpolate. So we did have that value just now. So this is at what temperature? Sorry. I should not be putting that here because there's no carbon dioxide in the inlet and no water vapor. So for what carbon dioxide at 150, you gave me the value. Carbon dioxide, where is it? Yeah, 4.99. That's 4.99. And for water vapor at 150, 4.275. Everything is there except for oxygen. Oxygen at 150. Oxygen 150. Oxygen 3.775. Yeah, you got that enthalpy done. Everything is done there. Your enthalpy over here also done. The amount of mole, you should get the same amount of mole. That's 100. That's 100. That's 376. That's 60. That's 50. 376. That's 30. 10 and 50. You have completed the table, but unfortunately, you still need to get your heat of reaction for number 1, heat of reaction number 2, and you need to get your extent of reaction number 1, your extent of reaction number 2 in order to do this part of the calculation. For the second part of the calculation, your table is already completed. No problem. Okay, so if you want to do this problem using the heat of reaction, you need to get the value of your heat of reaction for both reactions and the extent of reaction for both reactions. You need to do that. And how are you going to do that? It's quite easy actually. Yeah, you need to do the meter balance actually. You have, not sure whether we have enough time. Do we have enough time? Yeah, we have. Give me just 5 minutes to do this. Input mole reaction 1 That's reaction 1. Reaction 2. Okay, and lastly, that's your output. Output mole. I'm in a hurry, so I didn't even write it correctly. Okay, we have the component that we have. We have methane. Oh, I need to erase that because I want to make sure that I have enough space for every component. I have nitrogen. I have formaldehyde. I have carbon dioxide. Yeah, that's nice. That's better. Okay, the input 100. The output 60. Yeah. The input oxygen 100. This is from the flowchart, guys. The output 50. And actually you can get this from your that table here. Tempting. This is 76. Okay, nitrogen is not involved in either of that equations. So don't worry about the reaction coming in and out. It's still the same. So your formaldehyde, there's no formaldehyde, there's no carbon dioxide, there's no water vapor in your inlet. But you do have the outlet. That's 30, that's 10, that's 50. Okay, now look at the equation. You have to look at the equation. The equation, there's 1, 1, 1, 1. Okay, so equation number 1, all of the coefficient is 1. So methane is being consumed, -1. Oxygen is being consumed, -1. Okay. Formaldehyde is being formed. Formaldehyde is being formed. Formaldehyde is being formed. Water vapor is being formed. So +1 and the extent of reaction. So that will be +1. Extent of reaction +1. Extent of reaction. There's no carbon dioxide being formed in the first reaction. Okay. For the second reaction, let's look at the second reaction. Am I going too fast? Second reaction, that's 1, that's 2, that's 1, that's 2. There's no carbon dioxide in the first reaction. Okay? There is carbon dioxide in the second reaction. So your methane -1, that's 1. Oxygen -2. So -1, -2. There's no nitrogen involved in both reactions. There's no formaldehyde being formed in the second reaction, but there is oxygen, carbon dioxide being formed, and also there's water vapor being formed. I forgot the coefficient. Let's have a look.
2 for water.
2 for water. Thank you. 2 for water and carbon dioxide 1. Yeah. +2 for water, +1 for carbon dioxide. So now, how are we going to go this about? Just look at it. Look at formaldehyde. What do you think is in the bracket?
30, it's the coefficient 1.
Okay, coefficient 1 is equal to 30. Come on. Okay, look at carbon dioxide. What is the bracket? What is in the bracket? The extent of reaction?
10.
10. What's 10? That's how you do the calculation. So the only thing left now is to get your heat of reaction. You get to use this heat of formation, or you're going to use this equation, heat of combustion. Combustion will be reactant, coefficient, heat of combustion, minus product, coefficient, heat of combustion. Remember, we did this at the very beginning of the topic, chapter 9. So you have two methods of going about getting your heat of reaction. You can use either your heat of combustion, or you can use your heat of formation to get your heat of reaction. It is not that difficult to use the heat of reaction. It's just that you have to go the extra length in calculating the heat of reaction and the extent of reaction. That's why it's better if you use the heat of formation method to solve this example when you have more than one reactions. Okay? Guys, any questions?
Clear, Doctor. Thank you very much.
Thank you. Welcome, Aiman. Any other questions? Any other questions? So as you can see, you can solve it both ways. It is possible. The only thing is that in this example, your life has been made easier because the material balance has been done for you guys. The amount of product coming out is there. But in the test, in your final, you have to solve for the output, the molar flow rate of the output. You have to do your material balance. And how to do your material balance is just what I just showed just now. You need to get your extent 1, extent 2, based on the conversion given, based on the yield given or selectivity given, then you completed this table. This table actually is your material balance. And the table that I just drew, that I just constructed now, the way I show you guys how to get your extent of reaction 1 and extent 2 is actually your material balance. You need to do this. That's your material balance. Yeah. Any other question, guys?
Doctor,
Yes.
if I want to determine the extent of reaction for methane, so extent of
Methane.
reaction, for reaction 1.
Okay, for reaction 1, you cannot use methane because the reason is because you've got 2 unknown here. Okay, you can have the equation done, no problem. It's 100 minus extent of reaction 1 minus extent of reaction 2, you went up with 60. But you cannot have one equation and 2 unknown. You cannot solve it. You can go to oxygen after that, 100 minus extent of reaction 1 minus 2 extent of reaction 2, because this is 1, this is 2, the same here, this is 1, this is 2, and you come up with the final answer, then you solve it simultaneously, then you can get extent of reaction 1 is the same as 30, extent of reaction 2 is equal to 10.
Okay.
Okay. Is it the same? Why is it 60? 100 minus, can it be 60? 100 minus 30 should be 70, isn't it? Isn't it? If this is 30, this is 10, should be 70, isn't it? Why is it 60?
60.
Why then? Did I do something wrong?
No, it's
No,
right.
that's correct.
Isn't it? Oh, yeah. But sorry, I must be so tired. It's minus 40, right? It's 60. Yeah. Okay. This is 30. It is 10. Or you cannot end up with 50. You can solve it using oxygen and methane. Got 2 equations, solve it simultaneously. But then, if you just look at one of the component that doesn't involve the other reaction, you can automatically deduct the, you can automatically arrive to the extent of reaction. For example, looking at this, automatically this one is going to be your extent 1. This is going to be your extent 2. Just looking at the table itself, you already know, without having to go through the solving simultaneous 2 equations. It can be done. Just that you just make it a bit difficult, that's all. Any questions? Normally when you have this material balance, you get this value first. You don't have the product here. You get your external reaction first, then you arrive to your product. That's how you get your material balance. That's the normal procedure. But in this case, the product is already given. So I'm just trying to show you guys that, how to get your external reaction given that your products are there. But normally you have to solve for your external reaction first. You are given, for example, your conversion, your fraction conversion, it should be given. Fractional conversion should be given in the statement of your question, or your yield should be given, or your selectivity should be given. These are the terms that you come across when you have multiple reactions. What is the other one? Yield, selectivity, and what else? That's it. Yeah. Fractional conversion, yield, and selectivity. So any questions? Any other questions? We need to recall back your multiple reaction in material balance. So you need to do the material balance first before you can proceed to the energy balance. Without solving the material balance, even though you know how to get your enthalpies, but having no values of your flow rate, you can't solve it. But still, you get points for getting the enthalpies. If you got stuck on the material balance, you proceed to get the enthalpy. At least you get some marks there. Okay? You just don't have the full marks, that's all, because you do not complete the material balance. But if you can get the enthalpy, for example, from the table or doing the integration, why not proceed to the and getting the enthalpies? Do not leave it blank. Okay, guys, any other questions? Any other questions? It's already 3:51. No questions? Counting. 1, 2, 3. Okay, guys, that's it for today. When is your third test? Anybody? I'm going to share the QR code. I'm going to. Okay, guys. When is your third test? Anybody? Do you know? 20th of January. Wow. Today is already the 5th, is it? Or is it the 6th? I lost track of the time. Oh dear, my God. Already it's a 4th. Okay, thank goodness it's one day. It's 4. So we have 2 more weeks cover the rest of the chapter of chapter 9. 2 more weeks. That's okay. That's about four meetings. Yeah, 4 hours. Not 4 hours. 4 meetings. That's about 8 hours. On the 20th of January, you'll be asked on, this type of questions. Multiple reaction, single reaction, heat of reaction, heat of formation, heat of heat of formation method, heat of reaction method, that sort of things. Yeah. So for the rest of you guys, if you have already scanned, thank you very much for your attendance. Somehow the number of students that we have is getting lesser and lesser by somehow, don't know. I seem to have other students that did not scan. Most probably they are not from my class. Okay, guys, I wouldn't mind you attending it, no problem. Okay, guys, thank you very much for your attention and your presence, even though it's online, and for your oh my God, I wouldn't be able to pronounce it. Participation. Okay. So, Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr.
Welcome.
Buklada bir yer.